So Aude, the floor is yours.
Yes, I guess you're seeing my slides. Is
yes,
that the case? Good.
That's okay. Yes, and also the pointer, so it's okay. Yeah.
Okay, very good. So yeah, thanks, Teresa and Maurizio. I think you nicely introduced the topic, and so that will make my task easier. So I'm going to talk more about mechanical properties and damage and fatigue life enhancement by using post-processing treatments on a more simple and more common alloy, the aluminum silicon 10 magnesium. And I'd like to acknowledge Juan Guillermo Santos Macias, which just started his postdoc at Ecole Polytechnique with Manas, and is my former PhD student that did most of this work in collaboration with Luzao, that was my former postdoc, that is now a professor, assistant professor at Wuhan in China. And two of my senior researchers, Olivier and Camille, that have been also working in close collaboration to Olivier more on the roughness work that I'm going to show, and Camille with Guillermo on this friction star processing work. This work is also done with a lot of people from Leuven, from the synchrotron. I'll show you some synchrotron data results, and you already see some of the stuff here. In Lyon and Université of Antwerp for TM, and in particular Osnid, who's my colleague here at UCL, that's also professor at Antwerp and is a specialist of TM. And Université Paris 13 for hot isostatic pressing. So a lot of different collaborations that I'll try to acknowledge as much as possible as we go along. But so just a few words about aluminum silicon 10 magnesium. This is the most popular aluminum alloy for additive manufacturing. So this is one that is basically on the market now. So the ones, the 70, 75 are starting to come in the market. But these ones are more already in the market and slowly decreasing in their amount of production because new alloys are coming up, and you've seen that in the previous presentations. So it's interesting for aerospace structural applications, but there is also interest for heat exchangers and these kind of applications. But here I'm focusing on fatigue properties, and so well, I will of course more focus on aerospace applications where this is quite critical. And in terms of mechanical properties, I just want to show you here what a cast alloy of that type looks like in terms of tensile strength, and what an aluminum silicon 10 magnesium by L-PBF looks like. And as you can see here, the strength of these L-PBF alloys is much more interesting than the cast alloys. And if you compare the microstructures of these alloys, well, that totally makes sense towards what we're seeing here in terms of difference in strength. As you can see here, the strength of these L-PBF alloys, the microstructure of these L-PBF alloys is very fine, while it's in the cast alloys, due to the difference in the cooling rates during solidification, we have a very different look in terms of the microstructure. Now, if we're zooming in a bit, what we can see here is that these alloys are have a very very fine microstructure indeed. You can see here the scale, and you have silicon-rich phases here that are definitely much smaller, and the alpha aluminum matrix. And if you're looking in the TEM, you can even see between these silicon-rich networks, you can see some silicon-rich precipitates in the matrix. So this justifies the difference in strength, and we have shown recently with a very small and simple model the influence this can have on the strength, and indeed these silicon precipitates are quite significant on that side. Now, if you compare these alloys to the 6061, which would be considered as the raw alloy used in these types of applications, you can see that the ductility of these alloys is much higher. And that is definitely an issue when you have applications where, of course, damage resistance, you should have materials that are ductile to be able to sustain, for example, bird strikes, as you can see in that particular bad situation in this image here, where you have failure here of the fans. So this is definitely an issue, and we should improve the ductility of these alloys, not to form them, because we don't want to form them, they're already formed, but to improve their ductility and crash resistance. Another problem with these alloys is this is a quite old work of Mauer, where they actually showed already a comparison of this 6061 alloy that I was just showing here, and its fatigue properties after L-PBF. Well, we have certainly improved the porosity levels in these materials, and so improved the fatigue resistance. However, we're still well below the raw alloys. And what's the reason for that? This is a commonly known fact in people working on fatigue resistance. Well, they know that porosities are, and in particular large porosities, are actually a source of initiation of fatigue cracks. And so if you look here, actually this is a tomography image. I'm going to show you a bit more of these later on, but we have here about 0.30%, 13%, which isn't much, as you would tend to say, but you already have these really huge porosities here that are lack of fusion porosities. So this is on an EOS machine, really optimized parameters. So you can really say that this is optimized condition, and we're definitely not into something that is unusual. The impression is, of course, that you have a lot of porosities, but that's the 3D effect. And also you have a lot of roughness on the surface. So, so one of the questions we ask is, can we do something about this level of roughness? And so that's something that Olivier Poncelet and Camille and the rest that are with us today what we're having a good look at. They built some walls and looking at bulk and the contour, because we know that maybe one solution to that would be to improve the contour of these material, or adapt the contour to improve the roughness. This indeed is a good solution, and that works quite well. In particular, it's better to do the contour first and the bulk. We have explained this in the paper. If you're interested, you can have a look. But what's interesting to see is that well, even in the best conditions, you're still in the let's say 5-10 micron range in terms of roughness. There are some papers in the literature where you go down to like 3 microns, but it's really hard to go below that. And also one issue is that if you're changing this offset here, which tends to improve the roughness, and this is done in some commercial alloys just for the look of it, that you have a lower roughness. Well, the consequence is that you will end up with porosities, subsurface porosities here if you're changing the offset. So there is, of course, a trade-off here. Large offsets so lead to this subsurface condition porosities, and these large offsets are conditions that lead to the lowest roughness. So well, the conclusion I could bring here is that maybe the roughness is something we have to live with, and eventually consider post-processing treatments. Typically, in the aerospace industry, in locations that are sensitive, they're actually doing post-machining. The second thing about fatigue, so we talked about roughness. it's these large poles. I was telling you that these are bad for fatigue life. Well, this is Guillermo, and he's been working with some people that are mentioned here from Leuven and from INSA Lyon to try to do in situ fatigue of these aluminum tin silicon magnesium samples. And let me try to start this video because I think I need to get off this. Yeah, and I got off a bit too much. Here we go. So this is the video of a projection of all the images that you get when you're doing growing a fatigue crack on this. And he's been able to identify that the origin of this fatigue crack is actually on a really large porosity. And you can see some of them here. It's impressive the amount of porosities that you have here, but just this is just due to the fact that it's a projection, so we're projecting all the images on one slice to have a 2D look. So you're really seeing that these fatigue cracks are definitely initiating on these large porosities. So we need to do something about these large porosities, and that's the second message. So let's consider some post-processing conditions, and the most common one is the stress relief heat treatment, hot isostatic pressing. And then I'm going to talk to you about another option that we envisioned, and that was the main topic of Guillermo's PhD, was friction stir processing. And I will talk about some aspects related to damage mechanism and fatigue improvement by friction stir processing. So, the processing conditions could be like you could start with an aluminum silicon tin magnesium as built, and then consider a heat treatment and eventually a machining. I mentioned that in regions of stress concentration, of course, and these one would be pertinent in a case where you would really need a high fatigue life. So the most common stress relief heat treatment is 300 degrees at 2 hours. But we've been considering heat treatments between 200 and 300 degrees Celsius. These ones are actually aiming at eliminating residual stresses. I think Maurizio was quite clear about the interest of reducing residual stresses, and one of the reasons is also for a higher fatigue life. Of course, that also matters when we are building the part to avoid the fatigue, to any problems of fatigue life. But a most common option is hot isostatic pressing. And so Rizao in Wuhan, in China, did with one of his master students a small study about simulation here of hot isostatic pressing. And the classical hot isostatic pressing is 497 degrees, 100 megapascals, 2 hours. So then there is a post treatment. And so he's been looking with his student at what are options in terms of hot isostatic pressing to try to reduce the porosity quite significantly. In particular, we're interested in these large pores, as I was mentioning. And so here is the result of the simulation as a function of pressure and temperature. And here you can see the porosity reduces significantly at 400 degrees. But you can see that if you apply quite a significant pressure, well, at 350 degrees, it might be interesting. So the most common way is 100 megapascals, but here we've been working at 350 degrees. So we wanted to test the potential of this 350 degrees hot isostatic pressing condition to avoid the major losses in strength that you can observe with the 497 degrees, and I'm just going to show you in the next slide. So we've been trying this 350 degrees. And the advantage with these 350 degrees is that you don't have this additional 200 degrees heat treatment, which is a two-step heat treatment in the hot isostatic pressing. And so here is what the tensile properties look like. So when we saw that, we were very excited about the results. As you can see here, after 497 degrees hot isostatic pressing, we have this large ductility with this huge loss in strength that I was mentioning just previously. Now, after this 200 degrees, 8-hour heat treatment, you can improve a bit the strength, and the ductility is not too bad. So this is reasonably accepted in the aerospace industry and is applied quite commonly on these alloys before application. Now, as you can see here, this 350 degrees heat treatment was really good in terms of ductility and giving similar conditions of strength. So we were very happy with that. But then when you're looking at the fatigue life of all these samples, and you see we kind of gave up on the 497 degrees heat treatment because it was really not good compared to the as-built treatment, as-built material. The 350 degrees, well, was lower, and this is probably due to the lower strength. Now, we thought that, you know, having reduced the porosity level, we would expect to have a better fatigue life. And so we looked into this fracture surface of one of these samples here. And as you can see here, well, this one actually shows here, and I'm going to zoom on this one. It actually shows here a porosity, but you can see this porosity seemed to have opened. So our feeling here is that this hot isostatic pressing actually closes the porosities, so you don't see them anymore when you're doing tomography. And I didn't show you any images, but we did confirm that it reduces the porosity level. But these are just closed; they're not sealed in any way, or that is at least our feeling today. And so basically it reopens and it's making a very fine and crack, as you can see here. My background was in friction stir welding, and so I definitely thought that this would be an interesting solution. Friction stir processing is a post-processing treatment that you can apply on friction stir on parts and combining with machining. And friction stir processing is just the same principle as friction stir welding, but for those who are familiar with that, but I'm just going to show that after, so don't worry if you're not. Well, it can be applied directly to the parts without any welding. Now, you could also consider combining this with welding different parts together, because sometimes, you know, the sizes of the parts is limited, and doing some machining. So there are many options in terms of combining that, but the advantage is it's all done on the same machine. So you're not moving machines, you're like you would do for the hot isostatic pressing. Let me walk you through a bit what friction stir processing is. So friction stir processing, you have a tool here that's made of a shoulder here and a pin here. And this pin penetrates into the material until the shoulder is on top surface, and then it kind of stirs the material and advances in that way. So that can be used for welding, but it can also process the material, make a friction stir zone, which is called the stir zone. And this zone is highly deformed and presents some specific properties, but I'm going to show you what it looks like when we are doing that on our aluminum silicon 10 magnesium. And of course, in all welding conditions, you have a heat affected zone, but we're not going to talk much about that one today. Let me show you just a short video of what this looks like for those, again, who are not familiar with the process. So this was done on our old milling machine some time ago. Now we have a brand new friction stir machine that has been funded by an ERC project here. It's a European project. So you're probably wondering, how can you do this on AN parts? Well, I wouldn't be doing that everywhere, but just in regions of stress concentration, that totally would make sense. And I'm taking here some examples of parts built by AM that you can find in the literature. You can see here that there are regions of fixing the parts to the rest of the structure. And in these regions of fixing, we know that this is regions of stress concentration. So it totally makes sense to like make a small tour here, friction stir processing around these, if this can be an interesting post-processing treatment, and I will show you just after that indeed we were improving the fatigue life, so it's an interesting treatment. And we used here the different parameters. I'm not going to show you a lot of details of different parameters, but just to show you that we had to optimize these. And so we finally selected the 1000 RPM and 500 millimeters per minute conditions. And if not mentioned differently, these are the ones that were considered, but we also tried another one. I'll show you minor results on this. In terms of damage mechanism, here are the microstructures of the different treatments that we considered as built, stress relieved, and stress relieved here at 250 and a stress relieved at 300 degrees, and then after friction stir processing. And so you can see that these two conditions lead to very highly connected microstructures, while here you have a much more globularized microstructure. And this will lead to very different damage mechanisms that explain the mechanical properties. So here, just to show you what this silicon-rich network looks like. So we did some FIP SCM with Thierry Douillard in Salion. And here is what the microstructure looks like. So this is a very nice image of this very connected silicon-rich network. And here is what it looks like in the pore smell pool and the heat-affected zone. And as you can see here, there is a difference in connectivity in these three regions of the house-built material. Here I'm doing a short quantification of that. So here the fine melt pools. This is the place where mainly damage will concentrate here because of the high connectivity that you have. So if you have a highly connected network here, and this favors damage in this region. And what happens in the heat affected zone? Some people are mentioning damage in the heat affected zone. Well, that can possibly happen if it's a very wide zone. In our case, it was a very small zone. We did have some localization of deformation and some cases of failure in that location here in an in situ tensile test. But this was not the main conditions of failure. It was mainly in the fine melt pool zone due to this high connectivity of the network. And so if you have a high connectivity of network, basically the network breaks. Here in the heat affected zone, I just wanted to mention here that we should be careful when we're talking about connectivity in the heat affected zone. When you look into these, it really doesn't look connected. But if you look at the larger scale, you actually have some connectivity in the heat affected zone. So we're really seeing in the heat affected zone that we have a bit of connectivity still. So I was still looking at the as-built material. Now let's look at all our heat treatment conditions. The first thing I'd like to mention and identify for you is the modifications of the tensile properties. And as you can see here, in the as-built material and the stress relief, where you still maintain this network while you have a low ductility. While here, after stress relief retreatment at 300 degrees and the friction stir processing conditions, you have really a very strong spheroidization of the microstructure. And this spheroidization leads to a difference in the damage mechanism. In this case, we're actually breaking this interconnected network. This is looking at a failed sample. Same for here, while here you have particle matrix decohesions. Sometimes you do have particle fracture as well, but mainly decohesion of the particle. So here we have a disconnected network, and here we have a connected network. So now if we're looking at the damage mechanism that I'm going to show you in some more details after, what you can see here is that nucleation of damage happens in these as-built and stress relief heat-treated materials. Number one, so the highly connected conditions at a very low strain. So this network is not capable of holding a very large deformations. And so it really fails quickly with very low strains. And so this leads to final ductilities that are very low, that you can also see here. And when we have this globularization, you can see that the nucleation of damage happens a bit later, and I'm going to make sense after of the difference that you have between these two conditions, FSP and stress relief heat treatment 2. And this leads to a much higher ductility in these alloys. So why do we have differences in nucleation conditions? Here is friction stir processing. Here is the stress relief heat treatment 2. And these were tested, and we had a look at statistics of area fraction of damage and damage counts per area. And what we can see is that the stress relief heat treatment leads to small damage, but at a short distance. So quite a lot of area of damage counts per area. So many situations of damage, while you have a lower area fraction of damage. And in the friction stir processing, we saw a lot of area of damage, but they're long distance, they're not very frequent. And this is related to the difference in the microstructure. And here, if you're looking at the void nucleation as a function of the true plastic strain in an in situ tensile sample, where you can see the evolution of damage here, starting very, very early into the friction stir process microstructure, but these microstructure are much more spaced from one another, so they can actually sustain more deformation. And here in the heat-treated samples, we have smaller particles, but they are more resistant to damage. So they nucleate much later and then sustain very little deformations when they have nucleated. So basically, we're ending up with a stress relief heat treatment that is very similar to friction stir processing in terms of static properties. So you would tend to say that probably was not so interesting to do friction stir processing. Stress relief heat treatment was more interesting in that perspective. They have the same utility. But then we went into looking at fatigue, and you hear all names of people that have helped us. This was the work on hot isostatic pressing that I've shown you already, just to show you that we're not really convinced about the solutions that we found for hot isostatic pressing. If you look at the porosity in these materials, you can see that as built, stress relief heat treatment 2 and FSP, well, these ones have very similar porosity levels, while the friction stir processing one has a very significant drop in porosity, 0.03% compared to 0.13. But more interestingly, these large ones are just gone here. So you don't have them anymore. You don't have large porosities. So that made us think that this would have a very significant impact on the fatigue life. And indeed, if you're looking here at the fatigue Wöhler curves, here is the as-built and stress relief. They have the same porosity level. Basically, these ones have the fatigue life that I've shown you from the Moore results of 2015. So these ones are, let's say, not so great. And they're influenced very significantly by these porosities as I've shown you previously. And then you have the friction stir process materials here, And you see here they have a very impressive increase in fatigue life that can go to a factor of 100 in some for some loading conditions. So huge increase in fatigue total life by friction stir processing, and no effect of these selected processing parameters. If you can look here, you have actually 500 millimeters per minute and 1,000 millimeters per minute parameters of friction stir processing, and basically we have the same conclusions. So really what matters is to suppress all these porosities and of course not get defects due to the processing conditions by friction stir processing, but that's quite evident. So here, that was just to show you once more. Well, I think I'm going to skip that one, and yeah, it works. Okay, so that was again to show you that after stress relief heat treatment, we have the same situation as what I've shown you in as build condition, and so it's really a porosity, a subsurface porosity that actually causes the nucleation here. So as build stress relief heat treatment, same debate, porosities that are causing failure. So here is also an interesting result we got with these in situ tests at the SRF, and we look at the crack length as a function of the number of cycles. And you can see here the stress relief heat treatment. Well, the nucleation of the crack is quite early on, and we actually missed a bit the beginning. We weren't expecting it to happen so early. And as you can see here, it's growing pretty much at the same speed as the friction stir processing material, but that actually nucleated much later. These are conditions of low cycle fatigue due to the constraints of the synchrotron. But what you see here is that it grows pretty much at the same speed. So we wanted to have a look at that, and so we did fatigue crack growth conditions here. And so these are standardized tests where we look at the fatigue crack. So I'm going to show you again here a nice little movie that is done by a camera looking at the crack. Oh, that didn't work. Yeah. Okay. So here is how the crack propagates into the S-built material as we're fatiguing the sample. And as you can see, the melt pool borders that you can see here on the screen, well, they are actually influencing and deviating the cracks. So we thought, well, that's quite interesting. So that should be mitigating the fatigue crack growth. And so we had a look at S-built material, friction stir processing, and stress relief heat treatment. And I don't know if you guys are familiar with this, but the ADN is basically the crack growth speed, millimeters per cycle, and here is the delta K in a way is the stress level. And as you can see here, the as-built material actually has a propagation of crack that is much faster than the friction stir processing and stress relief. Here in this case, friction stir processing and stress relief are together. So we wanted to make sense of that. And for that, we looked at different effects, the deviations. And as you remember, I've shown you that in this movie that we have very nice deviation with the S-built material. And this is also observed a bit in the stress relief heat treated material, and in the FSP material, of course, there is none of this microstructure, and so the crack propagates very straight. So this will be in favor in low crack propagation in as-built and stress relief heat treatment materials. We thought there must be another explanation for these properties. We simulated the plastic zone in front of the crack tip, and one thing that we can definitely think of, due to the lower yield strength of the material, the plastic zone is larger in front of the crack tip for the stress relief heat treating material and the FSP material, and these are favoring plasticity induced crack closure, so closure of the crack while you're while you're propagating the crack, and this really slows down the crack, causing some compressive stresses in front of the crack tip. So this could be one of the explanations. What we think is one of the most interesting effects is this crack branching. And so here, as you can see, as built material, well, the crack is just sometimes deviating a bit due to the melt pool, but as I told you, quite in a minor way. But there is no branching. The crack is just going in its direction. While here in the stress relief material and also in the FSP material, well, actually what happens is you have some of the cracks that are branching here, and this, of course, slows down this crack propagation. And this is, if you're zooming a bit on these locations here, well, this can also be associated to the difference in the damage mechanism that we have already seen in my previous explanations about damage conditions. So definitely, we can explain the lower fatigue crack. Sorry, the pointer is a little bit slow. We can explain the lower fatigue crack growth in the stress relief and FSP materials based on maybe a bit of plasticity-induced crack closure, but of crack branching. So the deviations that I've shown you at the beginning is only a minor effect here. So this brings me to my conclusions, and so I've shown you that a bit about L-PBF microstructure and damage mechanism. We've done some nice 3D characterization of the silicon networks. Damage and ductility is linked to the presence of this network, and the strength is linked to the fine silicon precipitates. I've just shown you that very shortly, but I haven't proven you that with results. And friction stir processing is strongly postulated as a valid post-treatment for fatigue applications, including the impressive utilization that you have going from 0.1 to 0.4 true strain at failure. It has shown a very significant reduction of the porosity, and this improves the fatigue crack nucleation and growth. And that's the most interesting aspect of the friction stir processing post-treatments, because of course the treatment, the stress relief heat treatment that I've shown you as a comparison is interesting in terms of ductility, but not in terms of fatigue. So that closes my talk, and I'll be happy to take any questions.
Thank you very much, Aude, for this very nice talk, very interesting. I suppose there will be some questions about that, and if not, I have also some questions. So Roland?
Yes, thank you very much, Aude. Very interesting, and maybe also I understand better the discussion yesterday on laser shock cleaning, that you asked me a question, because that could be a way also to improve fatigue life on these products. So but then if I was just wondering, in the friction stir processing, how deep do you need to go? Your pin has a given depth, I think. Does it go through the full thickness of your product, or it depends on where the damage occurs, I guess, typically in fatigue conditions? But can we imagine, if you have a thicker product, that you would just treat the near surface region, and that would be enough to improve the fatigue life of your component?
It's a very interesting question, Roland. We've been, well, Camille is currently investigating that, actually. We continue having a more industrial project on this. This was more the scientific part of it. And in this industrially based project, we're really thinking about that. And I think I would tend to agree with you that you could probably treat the surface, because we know that it's subsurface porosities that are usually initiating fatigue cracks. So we believe that indeed, if you're just looking at the surface, that will be more than enough. Maybe it would even be enough not to have a pin, just have the shoulder part that could possibly be sufficient. So still something we're investigating.
Okay, thank you.
Okay. One question, Aude. I was just surprised with the ductility because you have practically no difference in ductility between the heat treatment and the FSP, but you have a very important difference in porosities. So that means that there is no effect of the porosities in this case, or?
Yes, I probably should have mentioned that. It's a bit more complicated than that because I think at certain porosity levels, so what you're mentioning is here the fact that these ones have very different in porosity and still have the same ductility. Yeah, so our feeling is that damage is mainly nucleating on this on these networks and
yeah.
Showing that here, so mainly it's the silicon network that causes the damage, but and we're looking at in situ tests in performed in the synchrotron and doing some tracking of these porosities and seeing how they influence the coalescence. So I'll have some answers, more detailed answer in the future. But our feeling at this stage of these results is that it does play a role in the coalescence mechanism, the porosities, I mean, because these porosities favor the final coalescence mechanism. But really at the early stages, not so much, and this is really what drives it. So I would say that the porosity doesn't matter so much a bit.
Okay, no, I understand, yeah, okay, I understand. Thanks a lot. Manas, perhaps for the last question.
Hi, Aude. Thanks for the talk. So my question is similar to what I had asked before during Guillermo's defense. So here, as you see, you start from an as-built material and then you friction stir process it, which reduces the strength but increases the ductility. And you say that damage is caused by, or you show that damage is caused by the silicon network, which in SLM would be much smaller in size in comparison to DED techniques. So if the goal is to improve ductility, why not try it with a DED approach where you already have the silicon network, which is larger in size. All the features become larger in size, but you still maintain the silicon precipitates, and you would already have a more ductile material with lower strength, possibly close to FSP.
Yeah, that's a good comment. I would tend to agree on that. Indeed, we started with L-PBF, but we could indeed do that on other processes. And we're actually thinking now we're going to wire arc additive manufacturing as well, but which is also expectedly leading to larger microstructures. Yeah, but what I think is very interesting is that in the past, so quite a few years ago, Florent Anarle was also with us at some point, is now postdoc, but did his PhD on, and in his PhD, he was looking at friction stir processing of 6061 row alloys. And he's actually shown that reducing the size of the intermetallic particles was also improving the ductility of these materials. So I think this is a quite general behavior. If you're reducing the size of very large particles, you can actually delay damage. And this is true in cast alloys as well. I mean, it has been shown in the literature, and that's what inspired us at the time, is that in cast alloys where you have these let me see if I can get it back, where you have these huge microstructure, these really huge silicon networks. If you break these down, actually it improves also the ductility. So this is a known aspect of friction stir processing.
Okay, so if you had small, so you want to keep the silicon particles small, but the network you want to have it big, and this is not something that you can achieve with DED because you also have the particles which are larger, right? Yeah,
well, if you have large particles, you of course have usually lower strength, so okay. It's always a compromise. These very fine microstructure are actually very perfect for strength, but they usually lead to, well, the very connected microstructure, I've shown you that these ones are very bad for ductility. But if you have very small microstructure in general, well, that's known fact in the material science, and it's always better. And so it's also better for the utility, because in that case well, it's known that small particles tend to break later. They need a higher stress to fail. So it's a commonly known aspects in damage, and so this will be interesting for improving if you can reduce the sizes.
That's a strong point for doing PBF and then FSP rather than going the DE route, right? Yeah.
And maybe change the conditions.
Okay.
Eric wants to.
yeah. No. I don't want to stop the discussion, but if there are no more questions, I think we can stop this session. Just remind that we will have, after the 3 talks this afternoon, we'll have one more time, half an hour to have the global discussion on the talks, on the today's talk. So I just thank one more time Teresa, Maurizio, and Aude for these three very interesting talks. And we come back on this session at 1:30 p.m.
I just have one thing to add.
Yes, Maras. Yes.
Yeah. So all these questions are going to be saved, and I will you will have the opportunity to repost them at the end of the day. So don't worry about it. Everything is saved. Okay.
Okay. And have a good lunch. And see you afternoon.
See you.